So one of the first things that I want to point out is the positivity of the energy eigenvalues. So let's do that. So how do we prove this? So to do this, let's revert back to the original expression of the Hamiltonian. So our Hamiltonian was p squared by 2m plus half kx squared. So just because we'll be using operators here, let me just emphasize that these are in principle operators. And so let's recall that if we have a Hermitian operator, which we are also calling self-adjoint operators, then this satisfies this. What it means is that for any pair of wave functions, so if we compute this inner product, then that's going to be equal to this inner product. So this is what it means to be Hermitian. So now H is, of course, a Hermitian operator because it's a sum of two Hermitian operators. Of course, X is a Hermitian operator, P is a Hermitian operator. Therefore, X squared is a Hermitian operator, P squared is a Hermitian operator. You can, one of the problems in your assignment is that if you have two Hermitian operators, say A and B, or if you have any two operators, they don't have to be Hermitian, and we take their self-adjoint, if you take their adjoint, then we get the reverse of the ordering of the operators. So, and of course, if they are Hermitian, then that's going to be equal to BA. Of course, if A and B are the same operator, then what we get is that if A is a Hermitian operator and we take its square and take its Hermitian conjugate, then we get back the same operator. So the product of a Hermitian operator with itself is also a Hermitian operator, and the sum of two Hermitian operator is also a Hermitian operator, and therefore H is a Hermitian operator. And of course, being a Hermitian operator means that its eigenvalues are real. But here we are going to show that not only is its eigenvalue real, they are positive. Okay, so let's get back. So suppose we have some state psi, and so for the sake of argument, we can take psi to be one of the eigenstates of the Hamiltonian. So that means that if H is acting on psi, it gives us E times psi. Of course, it doesn't have to be. So let's take the expectation value of H with respect to such an eigenstate psi. Then what does it mean? It means that we are computing this thing. But what is this? We can divide the Hamiltonian into its kinetic part and the potential part. Then we get that this is going to be, the first term will be 1/2, 1 over 2m, and psi. So let me not forget that hat. P hat squared of psi, and the second term is going to be 1/2 times k psi, k hat squared psi. Now, because they are Hermitian operators, what we can do is that we can write them as, we can factor out one of the p's and bring it over here. So we have this, plus we have k. Similarly, over here we have x acting on psi, x acting on psi, the inner product. So now let's call the state phi, by state phi, p acting on psi. So this is some state, and let's call by chi, x acting on psi. Then the expectation value of the Hamiltonian that we are calculating will be given by 1 over 2m, the expectation value, the inner product of phi with itself, plus half of k, the inner product of chi with itself. But we know that on a Hilbert space, for any state, its inner product is positive definite. It's only 0 if, so this is, this is 0 if and only if the state itself is 0. So that means that, okay, so this is positive. Similarly, this is positive. So this is a positive quantity. These constants are positive. Therefore, we see that h of psi is greater than 0. And of course, this is nothing but, if we are taking psi to be an eigenstate, this thing is nothing but one of the eigenvalues, and therefore the energy is positive definite.